This is a lecture series that takes place after the sticky tape lab, and so we will just be going through what we found in the lab and how that relates to chemistry. So in lab, we took a piece of tape, or two pieces of tape, and we stuck them together, and then we ripped them apart quickly. So that's what we see here. We have the tape before, and then in contact, and then separated. Well, we want to know what is happening with the electrons that originally started here and here, and then what they look like when they're in contact and when we rip them apart. So on the macro scale, the scale that we see, opposite charges attract each other, where similar repel, and neutral objects are attracted to all things but have no force on other neutral objects. So using these, we can figure out the charges of the pieces of tape, the foil, and the paper. So on the particle scale, if we're looking at what was the original charge on the tape before we peeled it off the desk, well, they normally cancel each other out, meaning that the positive and the negative balance out. It can be charged when some of the positive or the negative pieces are transferred or moved. So what we see here is some of the tape have electrons and they give it to the other piece of tape. And in doing that, we can make positive and negative charges. So here we have what's called a cathode ray tube, and what we're trying to figure out is the small movable parts inside of an atom, are they positive or negative? So looking at this, this came from a guy named J.J. Thomson, and he figured out that this little movable piece inside of the atom was either positive or negative. So let's see how he. We notice that when he has the positive sign down here, he thought originally that these little pieces were positive. That was his thought. So they should want to go towards the negative side. So we see this. But what we saw in his experiments were that time and time again they came down here to this, towards the positive side, towards the bottom, and this area here glowed really bright. So we definitely know that they were affected in some way by something to make them to bend down. If they were not charged, they would just fly straight across. So this is the neutral. Up here would be positive charges, and here would be negative charges. But he was so confident in his idea that these little pieces inside the movable parts of the atom were the positive pieces that he concluded that maybe gravity caused them to fall down, and not that it was a plus sign. To fix that, he decided to change his charges on his little cathode ray tube. So thinking if these pieces were affected by gravity, again we should see them heading down here. But what we really see is that once again they curve towards that positive side, and we saw a lot of hits up here towards the top. Since they went down when the bottom one was plus, they were hitting down here. And then now that the top one is plus and they're hitting up here, we can conclude that this little movable part is really a negative piece of the atom. Okay, so let's learn a little bit about the guy. J.J. Thomson, he did these experiments in the 1890s using a cathode ray, and what he found were that negative charges were the ones that can move around in an atom, and this is kind of like our key important idea here. He then decided that the rest of it was positive. So you have kind of this positive mass or goo or dough with little negative charges tucked in and around. He called this the plum pudding model, which is pretty gross. I mean, you can see it here. It's more like a bread or a really heavy cake than actual pudding. But they have little plum pieces, and they're kind of hard to see. So there's a plum piece there, and a plum here, and a plum here. So this is plum pudding, really popular back then. The positive pieces was the whole dough. So this positive piece is like all of this stuff in here, and then the negative charges came from these pieces of plum that are hanging out here. I don't personally like this this model. I like to chocolate chip cookies. So this is a little easier. So the dough, all of this stuff is the positive part. Okay, so we just have a bunch of this positive, and then we have these little negative charges in here, so you can see them much better, I think. Okay, these would be the negative. So positive cores and negative chips. Okay, some interesting facts about dough that also apply to our atoms. Sometimes the choco chips fall out. This makes the atom positive. If we lose those negative charges, we get, there's more positive left in there, so we have a positive charge. Some dough can attract extra chips. So when we get extra chips, that's putting more negative charges in, we have a negative charge overall. Some choco chips can move around in one ball or be transferred between balls. So we can have cookies that can have all of their chocolate chips on one side, or a few of their chocolate chips can go to the other atom. Choco chips repel other choco chips. That's because they have a negative charge. So they want to get as far away from each other as possible. Okay, cookie versus tape. So a normal dough has a perfect balance. If it has 3 positive, it has 3 negative. So that way they balance each other out. But some dough loses its chips and becomes chip light or positive. Some dough gets extra chips, that would be chip heavy, and it's left with a negative. All right, how does this relate to our tape? Well, in the sticky tape lab, which side of the tape has a higher attraction to the electrons? Sticky side or the smooth side? Well, the one that was negative liked the electrons, so it grabbed them. So we see when they were combined, some of the top tape's electrons jump down into the bottom tape. But so when they were ripped apart quickly, we took it apart so fast that these that these electrons didn't have a chance to go back home. See, when they're in this spot, they are still overall neutral because there's the same number of positive and negative pieces. When we separate them like this, we see that the top is slightly positive because there's the same number of positive charge here than there were in the contact or before adhesion, but now they have less electrons in there. So we have fewer electrons than what we had here to begin with. Down at the bottom, this is negative because we have more electrons. If you notice, there's more electrons here than there were here in the beginning. So this just kind of reiterates what we were talking about, and you can see the pictures are a little more clear. So the bottom tape has the same positive core, but extra electrons. This makes it negative. The top tape has the same core, but fewer electrons. So this makes it positive. So when we were looking, let's look at what happens with the foil and the paper. Both the foil and the paper were attracted to the top and the bottom. So since they were attracted to both of these and not repelled by any of them, they must be neutral. Okay, so they're neutral. The tape and foil interaction was much stronger than the tape and the paper. And there's a difference with this because one is a conductor and one is not. Here we have just a little particle diagram drawing. If you wanted to draw these, that would be great. We are going to talk through them here in your notes, so you don't necessarily need to do this. I have put a link to this PET simulation on Canvas, so if you'd like to go there and look at it, that's fine. So what we have is a sweater and without a shoulder apparently, and this sweater has a bunch of positive and negative, but we also have a balloon that we can rub on the sweater, and then it picks up the negative charges. And then there's a wall with various charges on it. And in this simulation, you can see what happens to the negative charges when this balloon gets closer to it. So I would like you to try this out. It does need to be on the computer, but it is a cool simulation to look at. Okay, so let's talk about what happens in a conductor. So in a conductor, the negative charges can move from one core to another. So we say that this is delocalized. So the atoms, we started out with 3 in each of these circles, but if you notice, this guy, he only has 1 left. That's because his electrons have migrated over and try to get as close to this positive charge as possible. So we see that the atoms here have more electrons. There's really more in there, and that's because the metal allowed all of these electrons to hop to different atoms or different cores altogether. In a paper, the negative charges are stuck. They're kind of held in place on their atom. So we see they try to get as close as they can, but they only can be on in their atom. So they just kind of hug one side to get as close to that positive as possible. Since we do not have the jumping like we had with the metal, we don't have as big of an interaction. This polarization on the paper is less pronounced than in the foil because these charges are stuck in their atoms. All right, so definitions. Obviously, there's a way to talk about one or the other. We've classified them as metals and nonmetals. So these metals, they're kind of like that loosey parent who doesn't, your friend who always gets to go out in the middle of the night and they never really have to explain where they're going. Well, that would be the metal with their electrons. If their electrons were kids, they kind of just say, okay, do whatever, jump, go over to this house, or all of those. Now, the nonmetals are kind of your more strict parents, and they have this really strong attraction, and they hold their electrons in, and they say, no, you can't go out, and you have to be home by 10:30, and all of that. So they're really, really strict on those, whereas the metals are kind of a little loose with their electrons and allow them to go pretty much wherever. What we have on your periodic table, if you start next to boring and underneath it is aluminum, what you want is to draw a line like this around those. And then you can see that next to it is SI, and you're going to go down and over, and you're just going to continue that down step and over step all the way until you reach the bottom. So this would be like AS, sorry, that's an A, and GE is tucked under here, GE. So continue down, you're going to go underneath AS and then down between SB and TE, and then underneath TE, and then down between PO and AT. So as this is going, it's just stair-stepping, like over one, down one, over one, down one. Mark that on your periodic table. So do this step. Here's just a side-by-side comparison of the conductor and the non-conductor. As you can see in the conductor, so this was like our foil and paper, we see that electrons are bouncing, they're trying to get as close to that positive charge as possible, and they can actually leave their atoms to do that. Whereas with the non-metal, they're straining to get as close as possible, but they really just can't go very far to get near this positive charge. This is why this whole process here is why we use metal for electrical wires, and we use rubber for their casings, because we want the electricity to go through the metal of the wire, but we do not want the electricity to go through the rubber of the coating. So these allow the electrons to move freely from one to another, is in the foil, and then not freely would be the paper.